Have you ever wondered why water expands when it freezes, unlike most substances? This is a question that has puzzled many of us. You see, typically, substances contract as they change from a liquid to a solid state. But water, ever the outlier, defies this norm. It expands, it grows, it takes up more space when it transforms into ice. But why is this so? What's the secret behind this unique behavior of water? Stay tuned as we dive into the science behind this fascinating phenomenon. To understand this, we first need to grasp the basics of matter and how it behaves. Matter, as you may recall from your school days, comes in three basic states: solid, liquid, and gas. These states are all about how molecules, the tiny particles that make up everything around us, interact with each other. In a solid, the molecules are tightly packed together, like dancers in a choreographed routine, each one locked in place but still able to vibrate a little. This gives solids their fixed shape and volume. Think of a block of ice or a diamond. In a liquid, the molecules have a bit more freedom. They're still close to each other, but they can slide past one another, allowing liquids to flow and take the shape of their container. Imagine a cup of coffee or a pool of water. In a gas, the molecules are the life of the party. They move around freely and quickly, bouncing off each other and the walls of their container. This is why gases can fill up any volume, whether it's a tiny balloon or a giant room. Now, when most substances transition from a liquid to a solid, when they freeze, the molecules slow down and get closer together. They take up less space, causing the substance to contract. For example, when molten metal cools, it solidifies and shrinks slightly, but water, it seems, plays by its own rules. The secret lies in the very structure of a water molecule. Let's delve a little deeper, shall we? A water molecule is composed of two hydrogen atoms bonded to one oxygen atom, often depicted as H2O. Now, if you imagine this structure, think of it as a Mickey Mouse head. The oxygen atom forms the face, while the two hydrogen atoms make up the ears. This isn't just a quirky representation, it's crucial to understanding the unique properties of water. You see, this molecule isn't symmetrical. It's what we call a V-shaped or bent molecule. The hydrogen atoms aren't opposite each other, but rather they're angled. This angle creates a fascinating phenomenon known as polarity, where the oxygen side of the molecule carries a slight negative charge, and the hydrogen side carries a positive charge. Like the poles of a magnet, opposite charges attract, leading to a special kind of bond known as a hydrogen bond. Now, hydrogen bonding isn't as strong as the covalent bonds holding the hydrogen and oxygen atoms together within the molecule, but it's potent enough to have a significant impact on the behavior of water. When water is in a liquid state, these hydrogen bonds are continuously forming and breaking, allowing the water molecules to flow past each other. However, as the temperature drops and water begins to freeze, something remarkable happens. The water molecules start to slow down, and these fleeting hydrogen bonds have more time to form a stable, fixed network. This network is not as dense as the random liquid arrangement. So, as water freezes and this network expands, the water expands too, against the usual rules of most substances. So, what's the takeaway here? Water's unique molecular structure and the presence of hydrogen bonding make it behave contrary to what we might initially expect. This hydrogen bonding is the key to water's expansion. And it's not just a neat party trick. It's a fundamental property that has far-reaching implications, which we'll explore in our next scene. When water freezes, these molecules arrange themselves in a pattern known as an ice lattice. Now let's delve into what this actually means. Water, as we've learned, is a curious substance. Its unique attributes stem from the hydrogen bonds between its molecules. These bonds are not static, they break and form, in a ceaseless dance. But when the temperature drops and water begins to freeze, this dance slows down. The molecules chill out quite literally, and they start to move less. This reduced movement allows the hydrogen bonds to hold sway, to stretch out and enforce their will. And their will is to form a structure, a pattern. This pattern is what we call an ice lattice. Picture a three-dimensional grid. Each point on the grid is a water molecule, and the lines connecting these points are the hydrogen bonds. The bonds insist on a certain distance between the molecules, a certain order. This order, this pattern, is a hexagonal shape. Why a hexagon? Well, that's a topic for another day, but trust me, it's a shape that fits perfectly with the properties of water molecules. Now here's the twist. This hexagonal pattern, this ice lattice, it's less dense than liquid water. It has more space, more gaps between the molecules. This is because the hydrogen bonds force the molecules into a configuration that takes up more space than when they were liquid and could move freely. And the result of this? The water expands, it becomes less dense. It's why an ice cube takes up more space in your drink than the water it was made from. It's also why lakes and rivers don't freeze solid from the bottom up, but instead, ice forms on the surface and floats. This curious feature is not just a party trick, it's a fundamental characteristic that has profound implications for life on Earth. And that's why ice floats on water. This unique property of water has far-reaching implications. It's not just a simple quirk of nature, but a fundamental characteristic that shapes our world in countless ways. Let's consider a few examples. In the throes of winter, when temperatures drop below freezing, bodies of water such as lakes and rivers start to freeze from the top down. This is because as water cools and turns into ice, it expands and becomes less dense, causing it to float. This creates an insulating layer of ice on the surface, beneath which water remains in its liquid state. This phenomenon is crucial for the survival of aquatic life. If water behaved like most substances, becoming denser upon freezing, lakes and rivers would freeze from the bottom up, potentially causing many aquatic species to perish in the cold. But the implications of water's expansion upon freezing don't stop at the water's edge. This property also plays a significant role in the weathering of rocks, a process known as freeze-thaw weathering. During the colder months, water seeps into the cracks in rocks. When the temperature drops and this water freezes, it expands, exerting pressure on the surrounding rock. Over time, this pressure can cause the rock to split and break apart. This natural form of erosion shapes landscapes, creating the jagged peaks and dramatic cliffs we see in mountain ranges. And let's not forget the implications for us humans. The expansion of water upon freezing can cause pipes to burst in winter, leading to costly repairs. It's also the reason why ice cubes float in your drink, keeping it cool without watering it down too quickly. So the next time you see an ice cube floating in your drink, remember the fascinating science behind it. Water's unique behavior when it freezes is more than just a curious fact. It's a fundamental characteristic that has shaped our world and continues to influence our daily lives. So why does water expand when it freezes? Let's take a quick look back. We began with the basics of matter, moving on to the special structure of water molecules. It's the V shape of these molecules that makes all the difference, allowing for the formation of an ice lattice. This structure, unlike in most substances, results in an expansion when water freezes. The implications of this are far-reaching, affecting everything from ice cubes to icebergs. It's all thanks to the unique properties of water molecules and the hydrogen bonds they form. And that, folks, answers our initial question. We've journeyed together through the intriguing world of matter, delving deep into the peculiarities of the water molecule and the unique structure of the ice lattice. We've discovered why water, unlike most substances, expands when it freezes. The answer, as we've seen, lies in the unique shape of the water molecule and the formation of a hexagonal lattice in ice that leaves more space between molecules. We encourage you to share this knowledge. Pass it on to your friends, your family, or anyone who might find these facts as fascinating as we do. Let's spread the wonder and the understanding of the world we live in. We're always here, ready to dive into more mysteries, more questions, and more answers. So, don't miss out on our future adventures. Click at Venkithateki on the screen and subscribe, please. Remember, there's always more to learn about the world around us. Until next time.